Okay. Hello, yeah, I'm Mihaela, and I'm going to talk to you today about using Fragment Hotspot Maps to drive the progression of fragment screening hits, and that's particularly in the context of crystallographic fragment screening. So in the past 2 decades, fragment-based drug design has shown to be a powerful tool for developing small molecule drugs and lead compounds. Screening fragments crystallographically can detect even very weakly binding fragments, but was historically unfeasible. But now there are facilities such as XChem at Diamond Lightsource near Oxford, which have made the process much more routine. And they can collect hundreds of fragment protein complex structures and process them within a week. But still, progressing these hits to higher potency leads can take years and is very expensive. So the question is then, how can computational methods help accelerate the process of progressing these hits? So once a fragment screening experiment has been done, what we have is an ensemble of structures of the same protein in complex with different small molecule fragments. And we can identify the hits, their binding mode, and the interactions they make with the protein. But it is difficult to rank the hits and decide which ones to progress and into which areas of the binding site. So the next step here is involves following up these fragments computationally. So that's exploring the adjacent chemical space and generating a hypothesis for the design of compounds that would have improved potency and selectivity towards the target protein, which can then be tested. And then this cycle goes around iteratively, hopefully leading to a potent and selective lead compound. So there is definitely great need for methods that can streamline hit prioritization and elaboration. So the first step in suggesting follow-ups involves which fragments to follow up and into which areas of the binding site. So fragments bind very weakly, and the binding often cannot be detected by conventional methods and assays. So as we know, the binding mode in crystallography, the focus is usually on fragments that make favorable binding site interactions, and also the ones that are tractable synthetically for downstream optimization. Yeah, the next step involves enumeration, so using the fragment as a basis as a basis to suggest prospective follow-up compounds. And then these need to be scored based on how likely they are to actually bind to the target protein, and docking is an often used way to do this. But many conventional docking functions are not parameterized to work with fragment-sized molecules, so methods that are specifically geared towards fragments are needed. So such as fragment hotspot maps. So looking at just the target fragment complexes can show what interactions of the binding site are exploited, and also give an idea of what further opportunities might be available. But not all interactions within the binding site contribute equally to binding. And in fact, you have these hotspots, which are areas and interactions within the protein binding site, which have a disproportionately large contribution to the binding affinity. And from the point of view of then choosing which fragments to elaborate and into what, in which areas of the binding site, it makes sense to prioritize the fragments and follow-ups that have good overlap with these hotspots. And the computational method I work with is called Fragment Hotspot Mapping, and it was first developed by Chris Rodeau while he was a PhD student at the CCDC. And it was developed specifically with the goal of identifying these key areas and interactions, and it encodes the information as binding site maps for a polar hydrogen bond donor and hydrogen bond acceptor interactions, with the highest areas of the maps that coincide with the interactions that drive fragment binding into the hotspot. So the way the method works is it starts by calculating superstar maps, which basically show the propensity for a probe atom. So in this case, a carbonyl oxygen, uncharged nitrogen, or aromatic carbon atom on around query groups on the surface of the protein, and this is based on interaction scatter plot information in the ISOSTAR database. These superstar maps are then weighted by the berryness of a point on the surface, as fragments tend to bind in pockets, and the resulting weighted maps are sampled by 3 fragment-like probes, which are rotated on the surface protein, and this takes into account the molecular context of fragment binding. And then the highest scoring points in the resulting maps co-localize with areas of fragment hotspots of the fragment hotspot binding. So in this case, it's highlighting the active site of the kinase and also the hinge pharmacophore interactions. So now we've looked at how a single fragment hotspot map is calculated, but the crystallographic fragment screening output is an ensemble of structures of the same protein in complex with different fragments. So we set out to determine how information from multiple hotspot maps can be summarized for a single target. And then we also wanted to have a way to look at differences between ensembles of closely related proteins, where the desired outcome here is to get a map that highlights areas that are shared between 2 related proteins, areas where we can gain selectivity for one versus the other, and also have some measure of the confidence in assigning them. The workflow for this involves first aligning the individual structures in the ensemble in the area of the binding pocket, removing ligands, waters, and ions, and then individual hotspot maps are calculated per structure. So throughout this presentation, the color coding is blue for the hydrogen bond donor map, red for hydrogen bond acceptor, and yellow for the apolar. The individual hotspot maps are then combined by taking the median value with some caveats we're going to talk about briefly at each point into an ensemble map. And then 2 ensemble maps can be compared to generate a selectivity map. And just a note here about the different types of fragment hotspot maps. The polar features are localized and directional, hence the more focused blobs that you see in those corresponding maps, and the apolar interactions are more dispersed, and they generally take up a larger area. So the hotspot map for each probe type is a 3-dimensional grid with a spacing of 0.5 angstroms. So actually, when we combine information from an ensemble of aligned hotspot maps, what we get at each point is a distribution of those of the scores for that point in space. And in some cases, many of these values could be zeros. This reflects local movement in the binding site, and it's quite common in the polar maps, as those features are smaller and more sensitive to motion. And we initially investigated 2 ways of combining the hotspot map, taking the maximum value sampled at a point, or taking its median value. And what we found is that both of those had their issues. So in the case of the maximum map, it doesn't take the frequency of the features into account, and so it holds the danger of overestimating the importance of features that may only transiently be there, or may essentially be noise. Whereas the median maps had the opposite problem of underestimating perhaps the importance of features, perhaps especially in larger and more flexible binding sites, where it could smooth over some of the more interesting hotspot features observed. Yeah, so in this case, the median maps would fail to spot the hinge kinase pharmacophore, which was worrying. So we needed something that could provide a compromise between introducing more false positives downstream, but was sufficiently sensitive to the polar features and contains information about how often a point is sampled. So we can define the frequency of a point in the ensemble, or in what fraction of cases there is a non-zero hotspot score at that point in space. And then points that have very few of these non-zero values can be filtered out by a frequency cutoff to reduce the noise and false positives. And we found that to work reasonably well for the ensemble maps. So now that we had a way to compile the information across an ensemble, we moved on to the question of comparing ensembles of structures of closely related proteins. So this is the workflow currently used to calculate the selectivity maps. So for each probe type, difference map is generated by subtracting the ensemble map for the off-target protein from that for the on-target. And then this next step, those maps can be filtered to only show the highest scoring points above a certain percentile of all the scores observed in the difference map. And generally, this is more important for the apolar maps as they contain a great number of low scoring points. And then features in the resulting maps are detected using the density-based HDV scan algorithm. And then the difference in this minimal points parameter reflects the differences in the sizes of the polar and apolar features specifically. Clusters are then also scored by taking the median hotspot score of all the points in that cluster. And there is also a condition that selective features be a minimal distance away from features of the same probe type that confer off-target selectivity. So that's to prevent having two selective features, two features with opposite selectivity next to each other, because that will not be desirable. And then to validate this method, I compiled retrospective examples of cases where a fragment or ligand has been elaborated with the goal of gaining selectivity over a closely related off-target. And in order to simulate a fragment screening scenario, I used only structures with bound ligands smaller than 300 Daltons. And then the selectivity maps could detect and prioritize binding site features that have been used to drive the development of selective compounds. So in this first example, we're looking at a precursor to the bromodomain probe BA299, which shows selectivity for the bromodomain BRD1 over the closely related BRPF1. And this compound makes a hydrogen bond with the backbone of serine 592 in BRD1. And that interaction is actually not available in the off-target, as the corresponding residue is a proline. And the ensemble, the selectivity maps can pick that up. So that's the area of red surface over here. And in this next example, we look at how the selectivity maps can pick up a hydrophobic pocket that opens up in the kinase P38 alpha, but not in the closely related kinase ERK2. And this is caused by the Bokeh gatekeeper residue in ERK2, which blocks access. And this feature is actually used by this compound SB1, which is a P38 alpha selective inhibitor. So based on the retrospective validation, what are some recommendations on using the ensemble and the hotspot maps in a live campaign? So a key thing to remember is that the ensemble maps are a tool for summarizing information and generating hypotheses based on it. And so they're only as good as the underlying data. So when compiling an ensemble, it's good to have a measure of its diversity. For example, are certain ligand types overrepresented, and that will then inform the confidence in the features that we see in the ensemble maps. Generally, for large ensembles, so in this case above 20 structures, a frequency threshold of 20% will identify the most persistent features. And the ensemble maps can be used on smaller ensembles as well. Around 5 to 10 structures would be kind of small, with the caveat that the features observed there will be more dependent on the individual conformations. And there it is especially important to also test these hypotheses with either experimentally or with complementary computational methods. So, for example, MD-based based methods could be used to also inform the reliability of these features. And then in the case of the selectivity maps, an ideal selective feature would both score highly and be located away from off-target selective features. So what does far away mean in this case? Well, in the Broadband domains, the features setting that threshold to 1.5 angstrom show to be sufficient, but for kinases, which, as we know, have more tend to be more flexible, we had to go up to 3 angstroms. So the recommendation for using this on a novel target would be to start at the high end to identify really the most prominent features, and then using smaller distances or lower score cutoffs again would need the caveat that there is less certainty involved, and it would be especially important to also to also use complementary methods. So what kind of complementary methods am I looking into? So to further investigate the behavior of hotspots in protein ensembles, I'm looking at applying this ensemble pipeline to snapshots of MD trajectories. So I'm interested in the importance of the opening of cryptic pockets to the hotspot profile, and then identifying transient hotspots, for example, which could contribute to the binding of fragments. Generally, investigating how much hotspots vary along the trajectory is is a very interesting question, as well as there is an expectation that hotspot interactions would be would be very persistent, and also something I want to explore is in cases where we have, for example, very few fragment structure, can the ensemble be supplemented with snapshots from MD trajectories? And then another method I've been looking into using is called dynamic undocking, and it's a steered molecular dynamics based method, which estimates the amount of work needed to reach a quasi-bound state where a key protein ligand contact, usually a hydrogen bond, has just been broken. And this value actually provides a measure of the complex stability of the protein fragment complex, and it's also ligand aware, so it's dependent on both the protein and the ligand. And it could be an interesting way to look at the stability that's provided by these rare hotspot interactions that perhaps we see in a subset of the ensemble, and also as a way to possibly evaluate the docked follow-up poses that score favorably with hotspots. So in terms of next steps, the ensemble and selectivity maps are being written up, so there's a publication in progress there. To rank and characterize hotspot features, as mentioned, I have been looking into using dynamic undocking to assess the structural stability of fragment protein complexes. Looking at MD trajectories, and this has been a bit slow with COVID restrictions, but trying to validate these in the context of a prospective medicinal chemistry campaign at the Center for Medicines Discovery at Oxford, and also analyzing data from current XChem projects. So in conclusion, thank you to all of my supervisors and everyone who's helped with the project. And thank you all for listening.